Yeah. So this is pulses for the purpose of transmission. Okay, so what we are saying is, supposing we had a string of ones and zeros. If we have a string of ones and zeros, so let us say we have this a stream 1 1 1 0 0 1 and so on and so forth. If we have this string, so one of the ways to write this would be one of the ways to represent this thing. Okay, to convert this would be what how should we do it? Bit sequence into electrical pulses. One of the ways should be that if we represent these ones by high value, let it be some value. Yes. So if I represent this by a high value as in, let us say, corresponding to 1, we transmit a pulse. So if we have obtained a 1, then we transmit a pulse. Okay, then we transmit a pulse, and let us say that this pulse is like this. Okay, of duration TB. Let this be the duration TB, and for 0, it remains at 0 level. So if this is the case, if this is the case, then how are we going to write this thing? How are we going to make this electrical pulses now? For 1, we will have the 3 ones. We will have this 3 pulses consecutive, one after the other, with which takes value 1. Okay, and this is called as, this is PT, pulse PT, and corresponding to 0, it takes value 0, and then again for 1, it becomes a pulse. For 0, it takes 0 value, and then it goes away. Okay, like this. So now if I actually see where is this thing going to fit in, if you actually see where is this thing going to fit in, okay, so this is basically done before this digital carrier modulation. This is basically done before digital carrier modulation. So this, why? Because if you see, remember, in ASK, PSK, and FSK, that is digital carrier modulation, even though we had it a uh, bit sequence coming from a source encoder, so we had to convert them into pulses. So this method of converting this bit sequence into pulses is again called as line coding. So actually, if I see, so if this is the source encoder, then we had this baseband modulation, also called as line coding, and then we have this digital carrier modulation, which is, we have studied ASK, PSK, FSK, like these. So in between these two blocks, we have this line coding. Okay, this is a portion of, so this is the message signal. This is the complete portion of the sorry, this is the portion of the complete communication transmitter. So this is the portion that we are going to study to this lecture. How can we perform these various line coding techniques? Okay, this is what we are going to study in here, and we have already done this one, and we are not interested in this one in this course. Okay, will not cover in this course. Okay, so this is how it goes. So at the source encoder, at this point we have this stream, and the output of the baseband modulation or the line coding, we want an output which should be like this. Okay, so that this can be fed to the digital carrier modulation. So where now after feeding this we can get ASK, PSK or FSK. Okay, is this point clear to everyone? Anyone who has not understood this, why are we doing line coding? Akash asking any specific name for TB. TB is the bit interval duration. Okay, this is the complete pulse duration. Anyone have any questions at this point so far? Anyone? Shweta, Gaurav,
No, sir.
Antariksh, Aditya.
No, sir.
Okay.
No, sir.
Are you all awake at this stage or not still sleeping? Am I making sense?
I'm awake, sir. I'm totally awake.
Okay, good, good. No one is speaking anything, so I got confused. Yeah. So now you have asked what is TV. TV is again the bit interval for which the pulse should be defined. So then in that case, this remains TB. Okay, TB. This remains TB. Yes. So similar thing can happen if we can map. Somewhat similar thing can happen if we map. There are various ways in which we can do the mapping. We can do for one and for zero, or we can map these two to do different pulses. Okay, we can map these to PT like this, and then we can map this thing at 0 to minus PT like this. Okay, so if this is the case, how is the resultant signal going to look like? How is the resultant signal going to look like?
The positive ones, I mean, the ones will give the same resultant, the zeros will give a negative pulse. That's it.
Yes, ones will give the same output, but the zeros. So if I now draw this one, so ones will be same. But for zeros, the amplitude level will no longer be zero, it becomes -1, like this. Okay, so it will continue like this in here. Yes. So this is, so the above one, it has been given a special name. This is called as on off, and this is called as NRZ. So the above one is has been given a name. This is called as on off or NRZ. NRZ stands for not return to zero. not return to zero, and this is called as polar. The next one that we have studied is called as polar. This is called as polar energy. Polar energy. So non-return to zero. Is it making much of a sense?
No, sir.
It is not making much of the sense. The reason being, it has been nomenclatured because the next thing which I'm going to tell you, excuse, a non-return to zero might not make sense at this stage. The next scheme that I'm going to, next line coding scheme that I will be discussing, then it will start making sense. Before that, I want to highlight a problem in here. So in both the schemes, that is, let us assume at this stage that NRG non-return to zero is the name given to them. And why is the name given to them? We will question this thing later. Before that, let us see this. What is the problem in these two, polar or on-off NRG? In this, if supposing we have a string of ones or a string of zeros, okay, then in that case the problem would be that this duration tb, how do you keep track of this tb? Supposing if you have 11 10 11 ones, okay, in this itself, so how is the signal going to look like? The signal will be a constant dc level, yes or no? A
Yes,
signal
sir.
will be constant dc level. So in that case the problem would be that how many ones were there. If there is a long string of ones, so then at this stage you might be thinking that if this duration is tb and there are 11 ones, so I can just have 11 times tb and that will tell me that how many tbs, how many bits were transmitted. But over the channel, if this is communicated over the channel, there might be delays as well, because there will be some communication delay. Okay, so if there is communication delay, which is always the case in the practical scenario, so then in that case it is easy to lose track of this number of ones for a string which has got a continuous ones or zeros. Is this problem making sense? Yes or no? Shrishti?
Sir, can you please repeat?
So I'm saying, supposing if we have a string of ones, if the input is supposing one, 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 like this. So the bit sequence inputted has complete ones. In that case, how is the going to be output? How is the line coded signal? The line coded signal will be nothing but just a constant DC value at one value. Okay, yes or no?
Yes, sir.
So in this case, because there might be because the channel itself is somewhat dispersive, so there will be delays. There will be delays as well. So then in this total duration, if you see, checking the total duration, you might get confused how many ones were transmitted. Yes or no? There is a fine chance, there is a fine probability where you can miss the count on the number of ones or number of zeros if there are a long string of ones and zeros.
Yes, sir.
So this is the problem in this case, in this case that you have studied. So this is the problem. So to overcome this problem, what could be the potential solution? To overcome this problem, what should be the potential solution? To overcome this problem, the problem is because if there is string of ones, there is monotonous, there is no change in the level. Okay, there is no change in the level. This is again, and another problem could be even if there are small number of ones, if the receiver has lost lost track of synchronization, that means the transmit and the receiver time are not exactly synchronized. Even in that case, this would be a problem. Even though there are some 3 bits only sent, or the small number of bits that these are ones, only these are sent. Only in that case, if the receiver has lost track of synchronization, there will be a problem. There will be a problem because again, it does not know how many ones have been transmitted. It can lose track of time. So in order to cater all these things, we say that in each bit duration tb, in each bit duration tb, the this line coded signal should return to zero. So supposing if we assume that this to be tb by 2, so in the first half whatever value it is taking, let us take this only. Let us consider the equivalent of on off keying. On off, sorry, equivalent of on off, not on off keying. On off. If I see the equivalent of on off, but in the second half, it necessarily has to return to zero. If in the second half, if it in the second half it necessarily has to return to zero, how is this going to look like? So it is going to be a pulse like this. Yes or no? It is going to be a pulse like this, even for 3 consecutive ones. It will always be a pulse like this, where in the second half of the duration, it returns to zero. Where in the second half of the duration, it returns to zero. And by doing this, what will happen? What can we achieve? By doing this, and for zeros, it will remain zero. Yeah, by doing this, can we eliminate the problem that was arising previously? Yes or no? So what we are saying in here is for 1 and for 0, and this is TB. What we are saying in here is that for the half duration, you have to transmit this pulse like this. So this is now PT. PT is not taking a constant value for the entire duration TB, whereas it takes for the half duration, it takes a non-zero value, and for the remaining rest of the half portion, it takes a zero value. And for zero, this is mapped to zero. So this is called as on off, but on off RZ, where RZ stands for return to zero. So is this NRZ and RZ nomenclature clear now? Is this nomenclature of RZ and NRZ return this clear now? Yes or no? Toshika,
Yes, sir.
how
Yes,
about
sir.
others? So this is basically return to zero or non-return to zero signifies whether within that bit duration TB, within the bit duration TB, whether the pulse is returning to zero or not. Okay, whether the pulse is going to return to zero or not. Similarly, if I have to, excuse me, yeah, similarly, if I have to make the counterpart of this polar NRZ to polar RZ, what will happen? Can we do that? For this polar NRZ, if we have to draw equivalent with eliminating the problem of this synchronization and losing track of time. So what can we do? What can we do? How can we proceed? So it would be, so in that case, 1 and zeros, ones should be so ones should be mapped to a positive pulse like this, which should be PT, and zeros should be mapped to negative PT, minus of PT, where pulses like this. And this scheme would be called as, what should be this? This should be polar RZ. This should be polar RZ. And for 1, we will have this as it is in the previous case, but for zeros, we will have negative like this. So this is how the signal is going to look like. Yeah. So effectively, and similarly, there is another technique which is called as yeah. So polar RZ, where we map 0 to minus TB, and so we can even have bipolar RZ. By the word a bipolar RZ, what do we mean is, so in here again, if I see, if I see in here, in the bipolar RZ, even in this case also, if there are a long string of ones, even then this could be a problem. This could be a problem. Again, this problem could be because of, again, a long string of ones, a very long string of ones. But even then, we can eliminate this as well by having another scheme which altogether says is called as bipolar RZ. And the way it is done is, this is polar RZ and this is bipolar RZ. For 0, we don't have any pulse. 0 remains to level 0. There is no pulse for 0. Which value should I take? 0, there is no pulse. Okay. But for 1, we have both the pulses. 1 rest, 1 can have both PT and minus PT. This or this. This is PT or minus PT. So the way in which it is done is, so whenever one come, it is going to change the sign. Okay, if previously it was transmitting PT for the first one, and then for the next one it should be transmitting minus PT. Okay, the pulse should be such a way that it should be minus PT. So this is how it is going to go, because in here this was 1 1 1 and then 0. Like this. So what will happen in here is that if I see this, so for the first one, if this was the positive PT, then for the next one it is going to become a negative PT, and then for the next one again, as the previous one it was negative, so this becomes a positive pulse PT, and 0 remains unchanged like this. And as the previous one had plus PT, so this one will have minus PT corresponding to this one. And then we have this like this. Yeah. So this is how this bipolar RZ is going to look like. So we have seen various situations and various problems, and based on these problems, there were various schemes, various line coding schemes that came up and overcome the overall problem of this converting bits into electrical signals. So any questions till this point?
Sir, if we have very long chain of 0, then we will not be using bipolar RZ.
If we have very long chain of,
0.
yes, I do understand the question that you are asking is, yes, in that case, because this portion will again be having a problem with the tracking. But the trade-off in here is, if you actually see why was this thing introduced, because for 0 in here, if you see that even for 0 you are doing some in here, it's not being done, but for 0 also you are doing some transmission, you are doing some power, you are wasting some power. So that's the only, so again there is a trade-off between all the schemes. Okay, so these schemes, if you bluntly see that these schemes are used in various places depending on, so it is basically between the understanding between the encoder, line coder, and the decoder. Okay, so each one have got their own positives and each one have got their own negatives. So based on that, these are used. The point that you are making is very valid, that the same can happen for 0 as well. But the motivation of doing this thing is to make to not to send anything in between zeros, and can still can cater to the long string of ones.
So mainly it was done so that we should not waste the energy at 0 pulses, means when
Yes,
it is
yeah,
0.
yeah.
Okay.
And plus, apart from this also, even for a long string of ones, even for a long string of ones, you can eliminate this problem. Why? Because now you are doing it alternatively, so it is more foolproof for long string of ones from polar RZ.
Okay, sir.
Okay, so if I overall obtained the power spectral density of these two, okay, polar and bipolar. So if I altogether obtain the power spectral density, so do people know what is?
Sorry, sir. One more doubt.
Go ahead.
S- Sir, then what was the disadvantage for this on-off RZ so that
So
it
in the
can be
on
used
of
instead
RZ,
of
yeah.
bipolar?
So in the on of RZ, there was again, if there is a long string, then again, so think it like this: on of RZ is if I see this one RZ, on of RZ with on of NRZ. So we know that on of RZ is better than on of NRZ. Okay. Now even then in this case also, if there is a long string of ones, so this will again be a monotonous pulse, but it is going to go from so in the first half and the second half, there is going to be the positive pulse and the negative pulse within the TB. Okay, so this is another way of doing it, another way of doing it. Okay, let us see this thing.
So,
Let us see polar and
sir,
bipolar case. So let us see the polar and the bipolar case, the spectral density of that. Okay, if I see the spectral density of that, if I see the spectral densities of the polar and the bipolar case, then it will make more sense. If I see the spectral densities of this is RYF of these two schemes, and TB was the duration, and RB is the bandwidth of that scheme. So if I see the spectral density and then compare polar and bipolar, if I see the spectral density and then compare polar and bipolar, so for bipolar, let us draw first polar. So for polar, it comes like this, and then again goes up. So this is the polar cases. But for the bipolar case, it comes like this. So this is RB and this is 2RB. So this is bipolar. This is bipolar. So if we actually see, the bandwidth for bipolar is RB and for polar is 2RB. So the bandwidth is again defined as the first zero crossing in here. So if I see the bandwidth of the bipolar versus polar, so there is a clear advantage of bipolar. Okay, there is a clear advantage of bipolar over polar. If we see the power spectral density, this is the, oh, this is not R, this is S. And SYF is the PSD. Various line coding techniques. Okay, if I see the power spectral density, then we can make it out. Then we can make it out this thing. So another important aspect that we have to look into is that if I see the total power of, if we see the sorry, not the power, the energy in these cases, if I see the energy in case where we are considering on off versus for polar. Okay, what is the energy? What is the energy in these cases? If I calculate the energy, if we calculate the energy, what can we see? What can we see in here? So for the first, for this case, what is the average energy? What is the average energy for polar RZ case? For polar RZ case, what is the average energy? And for the bipolar RZ. So first of all, if I see, okay, forget about bipolar at this stage. If I just compare the simplest case, which is RZ, polar NRZ, sorry, NRZ, polar NRZ, and polar RZ, and polar RZ, yes. So these three we want to compare and then see. So if I see this, and the above one, this, and this one. Okay. First of all, in the above two, in the case of NRZ, what do we see? How many levels it is taking? It is actually only taking how many levels?
2.
It takes only 2 levels. Where whereas whereas in this case it takes, in this case for the case of polar RZ, it takes 3 levels. Is it or not? It takes 3 levels. So, and now if I have to calculate the average energy, and we say that ones and zeros are coming with equal probability, if we see, if we say, okay, if you want to calculate this E average, and assuming, let us say that this AK belonging to 1 and 0, where probability of occurrence of 1 is same as the probability of occurrence of 0 is equals to 1 by 2. If I say this, then what should be the average energy? What should be the average energy for on-off case? For the on-off case, what can we say? What is the average energy? E average is nothing but, what is the average energy? How should we calculate it? So whatever value it is taking in the interval, so the way in which we can write it is that, so value which is being taken in the interval for 1 is 1 square, okay, times its probability, which is 1 by 2, plus the value which is taken by equivalent of 0 bit, which is 0 whole square, times its probability 1 upon 2. Yes or no? And we, so because these both are equally probable, we have multiplied this thing by 1 by 2, 1 by 2. What is this value?
Half.
This is half. Similarly, if I calculate this average for the polar case, what is the average value?
0.
Polar case E average. Will it be
That's
0?
half.
Will it be half? 1 upon 2 times 1 square plus 1 upon 2 times minus 1 square. Is it or not? For the polar
Yes, sir,
case,
yes,
it
sir.
is going to take either plus 1 or minus 1. So effectively, what is going to happen? What is going to happen? What is this value?
1.
1. If this is 1, so what do we want? We want that these signals, in any case, if you want to make the average energy for all the signals to be same, then we have to make some minute changes in here. So what is the need is for the polar and on-off to have equal energies, to have equal energies, to have equal energy, we have to make some changes. So what we have to do is, what the question that we are posing is, if this has got equal energy E average for polar and on off. So let us say this is polar, P for polar, and this is on off. Uh, okay, if I say this, so for this to be equal, let us say, implying that E average polar should be equals to E average on off. Let us say this is equal to 1. So we are trying to do this thing just to ensure, or just to see or conclude the result. So let us say if the energy, because if the energy in both the pulses are not same, that means the transmit power, or the energy that you are sending in the each of the pulses, in each of the stream of the pulses is not same, then you cannot compare the two of them. Yes or no? If you are sending more energy on one and consuming less energy on the other, then you cannot compare the two of them. So to make it a fair comparison, what we are saying is, if you equal the energies of the two of them, then what should be the various amplitude levels in the two of the cases? For the polar case, we have taken as it is, that means energy is 1, so this remains unchanged. But for the on off case, if we take the energy as 1, then what should be the equivalent amplitude level for the on case? So the question that we are asking is, when the average on off is equals to 1, then what is the pulse amplitude?
Sir, root 2.
Yes, yes. How do you do that? So that is simply because in this case, if I have, instead of 1, I had root 2. If I had in here, instead of 1, root 2 whole square plus 1 upon 2 times 0 square, so then this would have resulted into 1. So effectively I had to have a pulse which has got this amplitude as 1 upon root 2. If I have this root 2, if I had this root 2, okay, then what we are saying for the on off case, let us again write this thing. Then what should be the amplitude of the pulse? We say this is square root of 2. So this implies for on off, for on off, there are going to be two levels, which is 0 and square root 2. And if we have for the polar case, a similar analogous would be having amplitude as 1 and -1. Okay, if I have the amplitude as 1 and -1, so then these are same. These will have same energy, not same. These will have same energy. Now, if I draw this and then compare, as in this is 0 and square root 2, 1.414, so it should be a little less. This is going to be 1 and -1. This is 1 and -1. So what do we see in here? For the same energy, what is the difference between the two levels? What is the difference between the two levels in the on-off case? What is the difference between these two levels in the on-off case? What is this value?
Root 2.
Is square root of 2. And what is the difference in the two levels for the polar case?
2.
This is 2. If this is 2 and this is root 2, can anyone tell us which one would be better and why? Which one would be better? Which one would be better? Anyone? Whatever comes to your
I
mind, you
think
can
the
speak.
first one will be better because it will take less delay time to change the mode from high to low.
Which one you said? You said on off or polar?
On off, sir.
On off. So Aditya says on off would be better. Anyone else? And the reason what he's giving is that it will take less time to change. Yeah. So anyone else? So before I ask this question, which one is better, you should be asking what is the performance metering, because depending on what is desired, which one would be better may change. So first of all, the thing which is desired is, if this the communication is happening between the transmitter sender and the receiver, okay, then what is the purpose of the communication? The purpose of the communication is that it should it should have least number of errors. Yes or no, Aditya?
Yes, sir. Yes,
Yes.
sir.
So if it should have least number of errors, then you should be thinking in the terms of confusing one level with the other. Because of noise, what will happen? That a level L1 may be confused with level L2 because of the addition of the noise. Okay, in that sense, now you again rethink what should be the best one, which should be the better one. Yes,
So
Srishti, do you have an answer?
in this thing, then I
Mhm.
will say that the second one is better because there is more gap between the two levels. So
Yes,
the noise
yes.
won't be able to
So
affect it.
yes, in this sense, if you see that the probability of one confusing with the other is will be less in polar case rather than in on off case. The simple reason being is that the two levels are far more separated in the polar case than in on off case. So that's why confusing one with the other would be less in polar than in on off. But understand this, they both are using same energy. They both are using same energy. They both are using same energy. Even then, the polar cases are better than the on off case, and that is what it is coming in here also. Okay, so bipolar, that was bipolar and polar are almost similar. Okay, so what the effectively thing was that even for the same energy, polar are better than bipolar. So I will just summarize this because you have less time, so I will just summarize this. So polar, we know, for the polar cases we know that it uses twice the theoretical bandwidth, and the other thing is we cannot do error detection plus correction. Okay, and it has got non-zero PSD at DC, that is frequency f is equal to 0. And the other advantage would be, so these are not the advantage, these are just the points. Okay, what we are observing, what we have observed for a given power, it has lower chances of error. I should say, okay, the energy. Okay, that eventually says implies low probability of error, low error probability. Now, likewise, if I have to say things about bipolar, if I have to say things about bipolar, likewise, so what are the points? First thing is, in the PSD, we have seen that the PSD is what? PSD is takes 0 at DC, that is at F frequency being 0, and it is bandwidth efficient. And the other point is that problem, what is the problem? Timing extraction for long sequences of zeros, and another thing is can perform one bit error detection or correction. And okay, so let's stop at this point. Let's stop at this point. We will resume this in the next video. Okay, thank you, everyone.